Before moving on with the discussion of the spin-lock alternatives that are presented in Anderson's paper, let's do a refresh on multiprocessor systems and their cache coherence mechanisms. This is necessary in order to understand the design trade-offs and the performance trends that will be discussed in this paper. A multiprocessor system consists of more than one CPU and some memory that is accessible to all of these CPUs. The shared memory may be a single memory component that's equidistant from all of the CPUs, or there may be multiple memory components. Regardless of the number of memory components, they are somehow interconnected to the CPUs. And in this figure, I'm showing an interconnect-based connection, and this is more common in current systems, or a bus-based connection, which was really more common in the past. Also note here I'm drawing the bus-based connection to apply to a configuration where there is only a single memory module. However, the bus-based configuration can apply to both of these situations and vice versa. The one difference is that in the interconnect-based configuration, I can have multiple memory references in flight, where one memory reference is applied to this memory module and another one to the other memory module. Whereas if I have a bus-based configuration in this case, the shared bus, only one memory reference at a time can be in flight, regardless of whether these references are addressing a single memory module or spread out across multiple memory modules. So the bus is basically shared across all the modules. Because of this property that the memory is accessible to all CPUs, these systems are called shared memory multiprocessors. Other terms used to refer to shared memory multiprocessors are also symmetric multiprocessors, or for short, SMPs. In addition, each of the CPUs in these kinds of systems can have caches. Access to the cache data is faster, so caches are useful to hide the memory latency. The memory latency is even more of an issue in shared memory systems because there is contention on the memory module. Because of this contention, certain memory references have to be delayed, and that adds to the memory latency even more so than before. So it is as if the memory is further away from the CPUs because of this contention effect. So when data is present in the cache, the CPUs will read data from the cache instead of memory, and that will have an impact on performance. Now, when CPUs perform a write, several things can happen. First, we may not even allow a write to happen to the cache. A write will directly go to memory, and any cached copy of that particular memory location will be invalidated. Second, the CPU write may be applied both to the cached location as well as directly in memory. So this technique is called write-through. We write both in the cache as well as in memory. And finally, on some architectures, the write can be applied in cache, but the actual update to the appropriate memory location can be delayed and applied later. For instance, when that particular cache line is evicted. We call this technique write-back.